This is Foundations of Math and Pre-Calculus 10, Chapter 6.4, and we're going to be looking at functions. Now, a function is a relation, but a relation is not necessarily a function. And here's an analogy. A car is a vehicle, but a vehicle is not necessarily a car, such as a truck. The property that makes a function different from a relation is that a function gives only one dependent value for each independent value. Now, this is easily seen when graphed, and we're going to abbreviate function as fn. So here we have a function. Here, there's two values for this independent value. So this is a relation. And here we have three values for one independent value. So this is also a relation. Here we only have one dependent value for every independent value. So this is a function. Now, when we say something is a relation, it generally implies that it is not a function. So it's strictly a relation. When looking at a graph, we use the vertical line test. And if anywhere on the relation a vertical line passes through two or more points, then the relation is not a function. Now here's a tip. It's easy to show when a relation is not a function, but it's not easy to show that a relation is a function. So here we can see that it's a function, but the graph is cut off. We have to look at the whole graph to make sure that it's a function. Here we can see that it's not a function. So the problem is this. Suppose that the upper part of this graph looked like that. So it's an ellipse. And clearly this is not a function because it passes through two values, two dependent values for an independent value. So that's why I said it's hard, because we have to check the whole graph. And we'll write that as that is because we must extrapolate beyond the graph. Extrapolate means to figure out what's going on beyond the visible part of the graph. Now, function notation. This looks strange at first, but by understanding why we use it, it will make it sensible. So we have y is equal to 3x plus 4, and that's in equation notation. And in function notation, it looks like this. Y of x, we say of, when something's in brackets, 3x plus 4. Okay, so we're just adding this. Now, we generally do this instead of this because we use x and y so frequently, we just write it down as an equation. However, function notation simply makes it clear what are the independent variables, and it should say what are the dependent variables, as well as the equation is a function and not a relation. So here's some example. Taxes. We can calculate taxes. That's T of P, which is the price, is 0.07 P plus 0.05 P. This is the provincial tax, and this is the GST. This is for British Columbia. We have MLS points. So the points, and I'm going to label this 1 because I'm using P again later. we have wins and we have draws. And losses don't count. So we get 3 points for a win plus 1 point for a draw. Okay, now we're going to do points in NBA, so that's why we're calling it P2. We have field goals. We have 3-pointers. And I know in NBA we put 3 PT. However, we don't want to confuse the 3 as a constant. So we just keep it all as letters. And then free throws. So we have 2 points for a field goal. We have 3 points for a 3-pointer. And we have 1 point for a free throw. And we can use our functions by plugging in a number as a parameter. So for example, if the purchase price is $10, we have 0.07 times 10 plus 0.05 times 10. We get 0.7 plus 0.5, and the taxes work out to $1.20. Okay, for an MLS team with 4 wins and 6 draws, we have 3 times 4 plus 6. We just plug it in. W goes here, D goes here. And we have 12 plus 6. So that works out to 18 points. Now we have the NBA points, P2. 9 field goals, 2 3-pointers, and 4 free throws. So we have 2 times 9, 3 times 2, plus 4. So we have 18 plus 6 plus 4, and that's 28 points. Now to help you in this section, you need to recall graphing and solving linear equations from Math 9. One way to graph is to use a table. So we just put in 0, 0 here, 0 times a half is 0 plus 3. And we can also plug in more values. 2 divided by 2 is 1, plus 3 is 4. 4 divided by 2. 4 times a half is the same as saying 4 divided by 2. So 4 divided by 2 is 2, plus 3, that's 5. Negative 2. So negative 2 divided by 2 is negative 1, plus 3 is 2, and negative 4. Negative 4 divided by 2 is negative 2, plus 3 is 1. Now we can plot these values. So we have 0, 3. We have 2, 4, and 4, 5. We have negative 2, 2, negative 4, 1. And here's our line. Okay, another way to do this is to graph from slope-intercept form. And to do that, we have the y-intercept. We start here. And for half, the rise is 1 and the run is 2. So we go up 1 and over 2. And to plot the backwards way, we go over 2 and then down 1. So we just do the opposite for the rise. And we can do that again, and we would get the same plot. You also have to know to find solutions. So if we have this function equal to 3.5 and we have a graph, we just need to find, I'll use this color here, 3.5. 3.5 is here. That's the y value, the dependent value. We take this dependent value, go down, and then we get our x value, x equals 1. So from here, you can say that x equals 1. We can solve this algebraically as well. So we have 3.5 equals a half x plus 3. We want to isolate the x first by moving over any constant terms. So 3.5 minus 3 equals 1/2 x. So 0.5 equals 1/2 x. And We can multiply by the reciprocal. So 2 over 1 times 0.5, and x equals 1. Okay, this is easier to see if we change the 0.5 to 1/2. And we see that the 2's cancel out. And that completes this lesson.